Welcome to this explainer. Today, we're diving headfirst into a hidden world that literally holds the key to life-altering medical diagnoses. We're looking at histopathology, and we're not just looking at it as some routine lab procedure, but as a delicate, high-stakes craft. If you've ever wondered how a raw piece of tissue is meticulously transformed into a perfectly readable microscopic slide, well, you're in the right place. Let's get started.
Okay, let's take a look at this. What you're seeing here is the ultimate goal of the sectioning process. It's a perfectly formed, incredibly delicate tissue ribbon resting on a microtome. It almost looks like a strip of translucent film, doesn't it? But that ribbon actually contains unimaginably thin slices of tissue suspended in wax. The sheer precision required to pull this off is staggering. And honestly, it sets the stakes for the laboratory technician's entire craft. Because one wrong move, or even just one slightly dull blade, and that vital diagnostic information, it could be lost forever. So here is our master craftsman's roadmap for today. We'll start with the art of microtomy, move right into perfecting the blade edge, then look at fishing out tissue ribbons, the adhesives used in slide preparation, and finally, how to fix common sectioning errors. Let's jump into Section 1, the art of microtomy, or slicing the unseen. Meet the rotary microtome, also known as the Minot microtome. Invented way back in the 1880s, this absolute workhorse is the most routinely used instrument in the lab for this job. Its primary purpose is to cut standard paraffin sections at a mind-boggling thickness of just 4 to 6 microns. To put that into perspective for a second, a single human hair is about 70 microns thick. We are slicing tissue incredibly thin, relying on the internal ratchets and wheels of this heavy machinery to give us absolute, perfect uniformity. But you know, not all tissues play nice. Enter this sliding microtome. Invented even earlier in 1789, this variation is actually notorious in the lab as the most dangerous type of microtome, and that's because of its completely exposed sliding blade mechanism. It's not used for your standard wax blocks. Rather, it's highly specialized for cutting incredibly tough specimens that are embedded in a substance called celluloid. Whether you're using a base sledge model where the block moves, or a standard sliding model where the knife moves, you need immense focus to operate this thing safely. Now this next one brilliantly illustrates how technology adapts to urgency. It's the cryostat, or cold microtome. Imagine that rotary microtome we just talked about, but housed entirely inside a freezing chamber at a bitter -18 to -24 degrees Celsius. The massive advantage here? Speed. The cryostat can freeze fresh, unhydrated tissues in just 2 to 3 minutes, totally skipping the lengthy wax embedding process. This is absolutely crucial when a surgeon is literally waiting in the operating room for a rapid diagnosis. Of course, a microtome is only as good as its blade, right? On the left, we have the plain wedge knife. Notice its solid, thick, triangular profile. That robust geometry is perfect for cutting those frozen or extremely tough specimens. On the right, though, is the biconcave knife, which curves inward on both sides. This incredibly sharp, fine-edged blade is exactly what you want when you're cutting delicate 5-micron paraffin sections on a standard rotary microtome. Moving right along to Section 2, perfecting the blade edge through honing and stropping. A true master craftsman knows that without a mathematically perfect blade, getting those beautiful tissue ribbons is just impossible. Now, what's really interesting about this slide is the stark difference between the two phases of blade maintenance. First step is honing. That's your hard sharpening. The goal here is to basically heal the blade, removing physical damage and gross nicks by moving in an edge-first direction against the stone. Then comes stropping. This is the polishing phase. Stropping removes the tiny metal burrs that form during honing. But to do this, the direction must be reversed to edge last or toe to heel, which smooths the metal out rather than cutting into the strop. When it comes to the honing phase, the material you use matters immensely. This right here is a Belgium yellow honing stone. Now, while labs might use Arkansas stones or fine carborundum for a badly nicked blade, the Belgium yellow is highly prized because it consistently provides the overall best sharpening result. Achieving that perfect, flat, aligned edge usually takes about 20 to 30 double strokes. Once it's honed, we move to stropping, which is typically done on a high-quality horse leather strap. This step requires a bit more endurance, usually somewhere between 40 to 120 double strokes. Remember, this absolutely must be an edge-last motion. The leather doesn't actually sharpen in the traditional sense. It cleans, aligns, and refines the microscopic edge of the blade. It gives it that razor-sharp polish necessary to just glide through the wax and tissue without tearing it to shreds. All right, Section 3, fishing out tissue ribbons. This is truly a delicate art. Let's walk through the craftsman's exact sequence here. Step 1 is flattening. You take that freshly cut, slightly wrinkled ribbon and float it onto a warm water bath. In about 30 seconds, the wax expands and the tissue flattens out perfectly. But, and this is a big but, don't leave it longer than a minute or two, or it'll overexpand and ruin the sample. Step 2 is separation, where you gently tease out the single best section using a pair of forceps. And finally, Step 3, fishing and draining. You take a glass slide that's been smeared with an adhesive, immerse it vertically, capture your tissue, and stand the slide up at a precise 60 to 85 degree angle for a few minutes so the water can drain away. Now, once the tissue is on the slide, it has to be thoroughly dried. And the lab actually has quite a menu of drying methods, depending on the tissue type and, frankly, the ticking clock. A hot plate set between 45 and 55 degrees Celsius or a wax oven works beautifully for your routine cases. Dealing with highly delicate nervous tissue, it's best to just leave that in an incubator overnight. But for highly urgent cases, a technician might carefully pass the slide directly over a Bunsen burner just until the wax melts. Talk about high pressure. Section 4, adhesives in slide preparation. Let's talk about the chemical bond. You might be wondering, how does that tiny, fragile tissue stay on the glass through all the harsh chemical staining processes that come next? Well, a lab has a whole menu of primary adhesives to choose from. The most common is actually Mayer's egg albumin, which literally uses egg whites for adhesion, glycerol to prevent drying, and thymol crystals to stop mold from growing. It's an absolute classic. Gelatin provides a firmer attachment, but it tends to absorb stains. Then we have Poly-L-Lysine, which is widely preferred for advanced techniques like immunohistochemistry, mostly because it guarantees zero background staining. Finally, sodium silicate is incredibly strong, but it can cause blackening if you're using silver impregnation techniques. So the craftsman really has to choose the right chemical glue for the specific test they're running. And finally, Section 5, fixing common sectioning errors. Welcome to quality control. So the crucial point is, even with perfect tools, things don't always go to plan. Imagine you sit at the microtome, you turn the wheel, and instead of a pristine ribbon, your tissue block just crumbles or it tears right out of the wax. What went wrong? Let's play diagnostic detective for a second. If your block is crumbling, it's often because it's mushy, meaning the earlier dehydration steps were faulty. Sections rolling up or wrinkling? Well, your wax might be too hard or your blade edge is compromised. And you definitely have to watch out for chatters. These are thick and thin parallel lines across the section, usually caused by microscopic vibration from a loose blade. Recognizing these flaws instantly and knowing exactly how to correct them is the true hallmark of quality control in the lab. We've covered a lot today. We've gone from heavy, dangerous machinery down to a microscopic 5-micron slice floating on a water bath, bonded chemically to glass. It really makes you think, doesn't it? The next time you or someone you love relies on a critical medical diagnosis, will you look differently at those lab results? Because the answers to our most profound health questions rely almost entirely on this unseen precision, perfectly sharp blades, and the meticulous daily craft of histopathology. Thanks so much for joining me on this explainer, and keep learning.